All right, let's dive into an organism that is a constant and fascinating challenge for both the clinical lab and for public health, Legionella pneumophila. If you're a medical microbiologist, this one's definitely for you.
Just a quick heads up on where this information comes from. It's all based on a comprehensive review we pulled together using a Gemini deep search. If you really want to get into the weeds and see all the primary literature, just check out the accompanying notebook document for the full citation list.
So we've set this up to follow a path that should feel pretty familiar, from the lab bench straight to the bedside. We're going to start with the core microbiology, then we'll jump into clinical diagnostics, cover treatment, look at susceptibility, and wrap it all up with infection control.
Okay, first up, Section 1, the microbiological and biochemical profile. Let's really get to know the fundamental identity of this organism.
So let's start with the basics, its formal address, if you will. Legionella pneumophila is a gram-negative bacterium sitting in the class Gamma proteobacteria. But as you're about to see, it has some really unique quirks that make it stand out from the crowd. And here's the classic clue you see at the microscope. Legionella pneumophila is notorious for taking up the safranin counterstain very, very poorly. So what does that mean? It means if you're looking at a good sputum sample and you see a whole field just packed with neutrophils, but you can barely find any bacteria, that lack of evidence is a massive red flag pointing straight towards Legionella. This brings us to its growth habits. Legionella is what we call a fastidious organism. You know, it's basically a picky eater. It's got very specific nutritional needs and just will not grow on your standard lab medium, like a blood agar plate.
The key thing to remember here, the absolute non-negotiable, is its requirement for L-cysteine. It just won't grow on blood agar. But give it some buffered charcoal yeast extract agar, or BCYE, which is packed with L-cysteine and iron, and it's happy. It's also oxidase positive and asaccharylitic, meaning it lives on amino acids, not sugars. And that's a direct clue about its intracellular lifestyle.
Now let's talk about its built-in defense system. Legionella pneumophilia naturally cranks out beta-lactamases. This makes things like penicillins and cephalosporins totally useless against it. And this is so critical from a clinical perspective. Why? Because if a patient with Legionnaires disease gets put on standard beta-lactams for their pneumonia, that therapy is guaranteed to fail.
Okay, so let's move on to Section 2. We're going to connect the pathogen to the patient by looking at the diseases it causes and, importantly, how we diagnose them.
You know, infection with Legionella pneumophilia can go one of two very different ways. On one hand, you have Legionnaires' disease, which is a severe, life-threatening pneumonia. And on the other, you have Pontiac fever, a much milder, self-limiting flu-like illness that just goes away on its own. The thinking here is that Pontiac fever is more of a reaction to breathing in bacterial parts, while Legionnaires is a full-blown invasion.
So that leads to the obvious next question, right? With such a huge difference in how sick a patient can get, how do we reliably and, more importantly, quickly confirm a diagnosis of the really dangerous one, Legionnaires' disease? Well, we've got three main tools in our diagnostic toolbox. Culture is the gold standard, of course. It's 100% specific and gives you an isolate to work with. But it is painfully slow. You can't wait up to 2 weeks to make a treatment decision. Then there's PCR, which is incredibly sensitive and specific. The downside? No isolate for susceptibility testing or typing. And then we have the workhorse, the most common rapid test, the urinary antigen test, or UAT. It's fast, it's specific, but it has one massive limitation. It almost exclusively detects Legionella pneumophila serogroup 1. A negative UAT absolutely cannot rule out Legionnaires' disease. You could be missing any other serogroup or even another species of Legionella.
All right, so once we've nailed the diagnosis, how do we treat it? Let's jump into Section 3, Antimicrobial Treatment Guidelines. And because Legionella is an intracellular pathogen hiding out inside our own cells, the choice of antibiotic is everything.
So, if we look at the Netherlands, the SWAB guidelines are very clear. First choice is a fluoroquinolone, specifically levofloxacin. And take a look at the dosage, 500 milligrams twice a day. The second choice on their list is azithromycin.
Now, let's compare that to the major international guidelines from groups like the IDSA and ATS. They also recommend levofloxacin or azithromycin, but notice that key difference in the levofloxacin dosing. They recommend 750 milligrams once a day. This difference in dosing strategy is a really interesting point of discussion among infectious disease docs.
Now, when it comes to kids, the choice is a lot more straightforward. Azithromycin is the clear drug of choice, and the reason is simple. We want to avoid any potential risk of joint damage or arthropathy, which has been associated with using fluoroquinolones in children.
Let's move on to Section 4 and talk about susceptibility testing and resistance. With Legionella, this whole topic is way less straightforward than it is for many other bacteria we deal with.
So why don't we do routine AST on our clinical isolates? It's a really good question, right? Especially with an infection this serious.
Well, the biggest reason is that we don't have clinical breakpoints that actually link an MIC value to how a patient will do. Instead, what we have from bodies like EUCAST are epidemiological cutoffs, or ECOFs. It is absolutely crucial to remember, an ECOF is not for predicting if a treatment will work. It's a surveillance tool we use to spot non-wild type strains that might be carrying some new resistance mechanism.
And here are those current ECAST ECOF values for the main antibiotics. If you get an isolate with an MIC above these values, it gets flagged for surveillance. But again, this does not automatically mean that drug won't work in the patient.
So how does it resist these drugs? Well, the mechanisms are pretty much what you'd expect. For fluoroquinolones, it's mutations in the drug's target, the gyrase gene. For macrolides, it's an efflux pump, basically a little pump that shoves the antibiotic right back out of the cell, encoded by the LPAB gene. What's really interesting here, though, is that this pump seems to be mostly specific for azithromycin. This makes older macrolides like erythromycin a really poor substitute if you're trying to test for azithromycin susceptibility in the lab.
Okay, this brings us to our final section, infection prevention and control. And for this part, we are shifting our focus completely away from the patient and looking at where this all starts, the environment. The single most important thing to get your head around is this. Legionellosis is an environmental disease. There is no meaningful person-to-person spread, so isolating a patient is useless. All of our prevention efforts have to be aimed at the contaminated water systems where this bacteria loves to grow and spread.
The modern way to do this, the gold standard, is a proactive water management program. This is a big picture strategy. It starts with getting a team together and literally mapping out the building's entire water system. Then you analyze it for hazards, you set up control measures like keeping the water at the right temperature or using disinfectants, and then you just continuously monitor those controls and have a plan for when things go wrong.
And that's our deep dive into Legionella pneumophilia. Hey, if you found this useful, make sure you subscribe for more explainers on clinically important bugs. We'd also really love to hear your thoughts and your own experiences with these infection control strategies. So please share your feedback in the comments below. Thanks for tuning in.